Alright, so this is chapter 13 quiz. Okay, first one. Grandfather. Okay, first one. A grandfather clock are designed so there can be adjusted by moving the weight at the bottom of the pendulum up or down. Alright, so here is a pendulum. Okay, so pendulum like this, right? So okay, so it's a pendulum. So this weight can move up and down. Which suppose you have a grandfather at home that runs slow. Run slow means take a longer time, right? To go one period, right? Very slow. Alright, so we know period equal to 2 pi L over G. Okay, so slow means this is big, right? T is big, which means slow. Let's say it's big, right? Okay, so which of the following adjustment of the weight would make it more accurate? So you want to make a T smaller, right? Just like this, right? Quicker, runs faster. Okay, so if you decrease this one, so what do you do? Okay, so only thing you can do here is you make the L small, make this guy small. Okay, to make this guy small so you can move up the weight. Okay, instead of here, you can move to here. Okay, so that you make this L small. Alright, so first one is raise the weight. Alright, second one, a ball vibrates back and forth from the free end of ideal spring. Have a spring constant. Okay, so this is your spring constant, K equal to 20 Newton meter. If the amplitude of this motion is A equal to 0.30 meter, what is the kinetic energy of the ball when it is this much from its equilibrium position? Okay, so this is amplitude and this is the spring mass system. Okay, mass, spring, this is A. So if you grab object here at amplitude location, kinetic energy is 0. Okay, so kinetic energy, ask you about the kinetic energy. It is 0 at amplitude position. Alright, number 3. An object undergoing simple harmonic motion has a maximum displacement. So A equal to 6.2 meter at t equal to 0. Okay, so basically like this, right? So when t is 0, object is at here. If the frequency of the oscillation is this, so this is your angular frequency. You see, if you read from the unit, you can tell this is angular frequency. What is the object's displacement? At here. Okay, so this one, well, we ask you about the position at a certain time, so you have to know the position time relationship. And this guy at t equal to 0, the displacement is here. Okay, so object at maximum displacement at 0. Alright, so based on this condition, we can tell xt relationship equal to displacement 6.2, and we use cosine omega t. Okay, so omega t, and this equals 6.2. Cosine omega here is 1.6 t. Alright, so just use your calculator to substitute t. So ask you at this time 3.5 seconds, right? 1.6 times 3.5 cosine this. Okay, one more thing you have to pay attention here is this: you have to turn your calculator to, when you calculate the cosine angle here must be in radian. Okay, so you have to turn your calculator into, instead of a degree, into radian, and then you can calculate this. Alright, just directly plug in and figure out what is your x value at this time. So key point here is write out position time relationship. Alright, Number 4, a simple pendulum has a period t. Okay, so pendulum, if it were used on planet X, where the acceleration due to gravity is 3 times what it is on Earth, what would its period be? Alright, so same thing here. Period equation 2 pi L G, right? Okay, so now everything keep the same, but G increased by 3 times. Instead of G, now it's 3G. So everything here will be T equal to 2 pi. So bottom you have, instead of G, it's 3G, right? So you have 3 LG. Okay, so 3G, you take a 3 out, right? So this is everything is the same, but you see you have a square root of 3 on bottom. So the period became square root of 3 times smaller. Alright, number 5. A 0.5 kg harmonic oscillator has a total mechanical energy. Okay, so this total mechanical energy. If the oscillation amplitude is this, what is oscillation frequency? Okay, so here frequency asks you about in the unit of hertz. Okay, so ask you hertz, right? We know we can figure out angular frequency. Angular frequency divided by 2 pi. Okay, so that is the hertz. All right. So how do we figure out angular frequency? Well, from this condition, right? So we know mass equal to 0.25 kg has a total mechanical energy. Okay, so mechanical energy equal to 1/2 Ka squared, right? And also you know that amplitude is 20 centimeter. Okay, so A equal to 20 okay, equal to 0.2 meter. All right, so now total mechanical energy is 4.1 joule. That is mechanical energy, right? And then this is 0.2. So plug A equal to 0.2 in this equation, you can figure out what is K, right? So K equal to, you see, just like this equation, plug 0.2 into A. So this is 2 times 4.1 divided by A squared, 0.2 squared. All right, so this is K. So once you figure out K, then you have M. So you can figure out omega. Omega is equal to square root of K over M. All right, and then plug omega into this equation to figure out your frequency. All right, so let's make some quick estimation, right? So this is 8.2 divided by 0.04. So 820 divided by 4, right, equal to 205. Okay, so this equal to 205 divided by mass is 0.25, basically times 4, right? Square root of 820. Okay, that is your angular frequency, right? And then plug angular frequency square root of 802. Let me think. Square root of 802. 820. I'm sorry, 820. Square root of 820 will be what? Square root of this one equal to 20, 2400, 25, 625, 625, 25, 30, 900. Okay, so roughly 828. Guess, right? So 14 divided by pi, 28 divided by 2 pi, right, equal to 14 divided by pi. Pi is 3, 14 will be, yeah, it's about 4. About 4. Maybe 4.6, yeah, maybe. Let me see the answer. Number 5, yeah, it's about C, yeah. Okay, number 6. If the angular frequency of the motion of a simple harmonic motion is doubled, by what factor does the maximum acceleration of the oscillation change? All right. So angular frequency is omega, right? And we know maximum acceleration equal to omega squared times a. Where do we got this? Okay, so there are several ways to get this. Okay, because acceleration equal to kx over mass, right? Okay, you see, then the maximum acceleration equal to kx maximum displacement over m. K over m is your angular frequency square, because angular frequency is k over m, square root of k over m. Okay, and then maximum amplitude, maximum displacement is your amplitude. That's it. All right, so now you double the angular frequency. You see, omega doubled. Then acceleration, maximum acceleration will be 4 times bigger. Okay, because maximum acceleration equal to omega squared times a. Number 7, in a supermarket, this is basically a weight, right? 22.3 Newton. This gives you mass equal to 22.3 over 9.8. Okay, so this is your mass, kg. You can divide by 9.81. Okay, so because weight equal to mg, m equal to weight over g. And the scale start to oscillate. So this is your frequency. Okay. All right, ask you the fourth constant, ask you k, right? Okay, so you know f, so you can tell what is angular frequency, right? Angular frequency, so equal to 2 pi times 2.7, and angular frequency equal to square root of k over m, right? So k equal to omega squared times m. Okay, and what is omega squared? Equal to 2 pi f squared times m, equal to 4 pi squared f squared m. All right, so so you can figure out what is k, right? Just plug in, everything's here. Keep that in mind. You have to use 22.3 divided by 9.81 to that's your mass. All right. Number 8, an astronaut has landed on planet N40 and conducts an experiment to determine the acceleration due to gravity on that planet. He uses a simple pendulum, that is, so this is L, and measures a 10 complete oscillation, 26 seconds. Okay, so that's a 10 complete oscillation. So t equal to total time divided by oscillations, right? Equal to 2.60 seconds. All right. So what is acceleration? Looking for acceleration. So from this equation, t equal to 2 pi L g, right? So looking for g. Solve for this one. So t squared equal to 4 pi square L over g. So g equal to 4 pi square over t squared times L. Okay. So L is, this is L. This is your t, right? Plug a t here. Just directly plug in, right? So this is 2.60 square. L is 0.640. All right, calculate that. Number 9, an object is undergoing simple harmonic motion of amplitude. All right, so it's amplitude. So A is this. If the maximum velocity of the object is this. Maximum velocity happens when object back to its equilibrium position. Okay, so this is the v maximum equal to 10 meter per second. What is object's angular frequency? All right, so how to figure this out? We can use energy conservation, energy equation, right? So at the extreme location, you have 1/2 k a squared. That's the total energy at extreme location, equal to total energy at equilibrium location. Okay, so at equilibrium location, you only have kinetic energy, right? All right, so half cancelled. So k over m equal to v maximum square over a square. All right, so this equation. And then you square root on both ends. Left side is your angular frequency, right? So angular frequency actually equal to v maximum over a. You see, give you v maximum, give you a. Directly, the ratio actually is your angular frequency. All right, 10 divided by 2.3. All right, so it's a 4 point something, right? It's more than 4, less than 5. Oh, I guess it's this one. I guess it's 4.3. Well, anyway, you can calculate this, right? 10 divided by 2.3. Yeah, it's about 4.3. All right. Number 10. A simple pendulum takes 2 seconds to make one complete swing. So you know t equal to 2.00 seconds. If we now triple the length, all right, t also equal to 2 pi L over g. So you triple the length, right? Triple the length. Now, which means this equal to 2, right? So you figure out what is 3, right? So this equal to square root of 3 times 2 pi Lg. This is 2, right? 2 times square root of 3. Square root of 3 actually is 1.732, right? So 2 times that is 3.4. Yeah, okay, so this one, right? Number 11. An object is oscillating on a spring with period. Okay, so this one, period equal 4.60 seconds. At time equal to 0, the object has 0 speed and is at this. Okay, so if you look at diagram, right? So this is t, this is at x equal to 0, at t equal to 0, the object has 0 speed, which means at extreme location, right? So this is 8.30 centimeter, right? So the curve will look like that. So this is a typical cosine curve. So x equal to A is 8.30 centimeter cosine. This is your t, right? So equation here 2 pi over t. Okay, so that's the equation. Now we plug in 2.30 cosine 2 pi, period here is 4.60 t. All right, so this is the xt relationship. Ask you what is the acceleration of object at t equal to 2.5. Now you can just substitute t here by 2.50 seconds. Okay, use your calculator, figure out what is your displacement. Okay, so figure out x, right? And acceleration a equal to kx over m. Okay, well, there's no, you don't know k, you don't know m, right? So this one, k over m, is your omega squared times x, right? And then what is the omega? Okay, so if you know t, right? So omega equal to 2 pi over t. You see, this is your omega. Okay, so because you know t, so you know omega. So plug omega here, and you plug your displacement by at 2.50 seconds here. That is your acceleration. Okay? Alright, so this is time. Give you time, and you can figure out the displacement from position time relationship. Okay, so this problem will take you a couple of steps to figure this out. Alright, so that's all for chapter 13 quiz.